So I already gave a talk I guess on Wednesday, but for those of you who may not have been here, I'm Seth Hitefield. I'm a graduate student at the Hume Center at Virginia Tech. I'm going to present some work that I've done for my PhD. So I'm specifically focusing on wireless security and SDRs, but I'm trying to come at it from a slightly different perspective than you may have seen in the past. So one of the cool things about SDRs is there are tons of awesome hacking opportunities, right? So, some of the stuff at the top, Balance done some pretty awesome stuff. I really love his pager one. If you haven't seen that video on YouTube, you gotta watch it, it's awesome. We saw some awesome stuff about drones. There have been some interesting Wired articles about hacking cars wirelessly. In fact, at the Hume Center, we've had a little bit of fun with that. If you want to know about it, ask us later. And also, there's been some interesting stuff about being able to use SDRs to jam wireless home systems and how insecure those really are. So there's just a very big and increasing proliferation of software-defined radio in the industry, which makes it an interesting opportunity because usually there used to be hardware radios, everything was in ASIC, and there was a significant amount of verification that was done for that hardware to make sure it operated as intended. With software, there is a lot of testing that is involved, but sometimes things don't always work the way they're supposed to. And now all of a sudden you have an FPGA, you have a host, you have software running on this, which means that there's a good chance that that software is exploitable from a traditional cybersecurity perspective. So over here on the right, I have just kind of a block diagram of several different types of components in a software radio. And towards the bottom, on the top right, you have the application and presentation layers, right, which are your traditional networking security areas that you typically find all of the traditional network attacks. And down here in the bottom, you have all of the SDR implementations, which could have bugs. And the point of my research is to look at that and to see what I might be able to exploit in a software radio from a cybersecurity perspective. But I'm actually looking at the implementations of the software themselves. So just a quick overview. The goals of what I'm trying to do is to find vulnerabilities in the software radio waveform. Not the protocol, but the actual waveform implementation itself. So typically that's going to be in the MAC or physical layers. And it might not be able to be detected through a traditional means that you would see with information security. Some of the other stuff is I've had a couple of demos. I didn't want to do one here because it was a shorter talk. And I'll talk a bit about 3 different classes of attacks. And I'm also doing some research into developing some tools to protect against these types of attacks. So the first one I want to talk about is a buffer overflow attack. So buffer overflows are common sources of vulnerabilities. There's been a lot of research on how you might mitigate against those on a traditional desktop or traditional cybersecurity platforms. It always happens when there's a fixed size or a fixed memory buffer, and then a write or to memory ends up overwriting the end of the buffer. Specifically, it gets really interesting when you're dealing with things like stack frames. So stack frames are automatically generated by the compiler, and they have tons of different things that they account for in the system. Arguments to function calls, the return addresses for when the function's completed, the base pointer, local variables of the function, those are all defined in the stack. And if you end up having a buffer overflow on this stack, there's a very good chance that you can end up overriding some important information that the system is using for control flow. And that's a lot of times where code injection and execution happens. If you're able to overwrite a buffer and then change the return address to point to that buffer, then you could in turn execute some shell code. Again, there's been a lot of research, so that's somewhat mitigated, mostly mitigated, I think. But return-oriented programming is another interesting aspect that can be exploited from this perspective. And that is where you set the return addresses in the stack very specifically to point to memory that has already been loaded and is already marked as executable by the system. So from a software radio perspective, let's assume that a fixed size buffer is used to store an incoming frame in the system before you parse everything. If there is something like improper length checking on that frame, and there's a specific length that the developer or that the application says, hey, this is the maximum length frame, but an attacker sends a frame that's significantly longer, what kind of things could happen? So for example, on the right here, I have a very simple example of what a memory layout might be. So you have the buffer in the blue at the top, and then down at the bottom you have two state variables. One of them is the index of some loop, and the other one is a state variable. Maybe it's used for an if statement or something like that. If you're able to overwrite the buffer with a frame that's too long, there's a good chance that you can corrupt some of those values. And if you do corrupt those values, there's some interesting things that can happen. So, like I said, let's assume that somebody makes the decision that a receive frame will never exceed the maximum transmission unit of the system. So here, if I have this simple framing structure with a header, length and checksum, some payload, and a trailer, if the attacker sends one that happens to exceed this maximum transmission unit, what ends up happening is I can corrupt memory. So I can either corrupt memory and cause a seg fault or a crash by changing the index value to where the next time the loop runs, it tries to access memory outside of its address space. Or if I am able to change the return address on the stack, there's a good chance that whenever that function returns, the system could crash. And that's an example of a type of maybe persistent jamming, that you send a single burst, cause the system to crash, and now the whole thing's down, and they have to completely restart the system in order to get it back up. Another type I want to talk about is header injection. So this is coming from the perspective of looking at the state machine within a radio. So for example, I found this in the wild. It's part of Liquid OFDM. And there are three specific framer synchronization states. There's a preamble synchronization, a header synchronization, and then a payload demod. So what the software does in this case is it incorrectly makes an assumption that every single one of these states will happen correctly and in order. So for example, what happens if I do an injection against the system and I send a correct preamble and I send the correct header, but then I don't send anything else? What I found was in a system like Liquid OFDM, this had a variable length packet, and it also had variable forward error correction per packet. So what I did was I was able to inject, so for example here you have normal frames coming through time, I was able to inject a single header that said, I'm sending you the maximum size payload with the maximum FEC so that you expect to receive the longest payload you can possibly expect. And then I just don't send anything else. And what I found is that this ended up being a type of low power jamming scheme, because the software never checked to make sure it was actually receiving a payload. It simply received what it thought was there, and in turn ended up losing several burst frames from the legitimate source. So if you know the maximum length payload, you know the time that the legitimate transmitter is transmitting, then you can inject these headers in between their burst and take the receiver offline for a significant amount of time. So the last thing I want to talk about, and this one I kind of found by accident. So recently, I think it was a couple months ago, we participated in one of the spectrum sharing challenges at Virginia Tech. And the Wireless at VT program had a cognitive radio testbed platform that we were using as the basis for the system that they implemented. It was also based on Liquid OFDM. And Liquid OFDM has a 14-byte header for every packet. And of that, 6 are used internally by the framing system, and then 8 can be user-defined. So I was trying to design a system that was adaptive in frequency, bandwidth, forward error correction, all these kinds of things. So I thought, hey, I'll just use the header, and instead of trying to transmit information like the actual frequency, I just created an array, and I just sent the index of the array. And about 2 weeks later, we were preparing for the next phase, and we talked about the possibility of if we could jam somebody else. And I realized that I made a huge mistake and opened my system up to being crashed. The reason why is because I assumed that the control bytes that I was using were always going to be valid indexes of whatever array I was trying to pull from. And in this case, I was using a byte, 256 values, and I was only using 6, 4, and 4 possible states that the system could be in. But an attacker could easily transmit a frame that maxed out the entire header. And had that happened, the set transmit frequency would have tried to pull from some completely random part of memory, which would be who knows what, and it would then try and set the UHD frequency. Now, there's a good chance that that may have worked, and then my usurp would have been in a completely unrecoverable state because I would no longer be synchronized to the rest of the system, or it could completely cause UHD to crash and in turn crash our application. So the assumption that, the problem was that I made the assumption that the bounds that were received would always be within the array that I had created. So that's the 3 of the different attacks that I've found so far and that I'm trying to expand upon. And the basic goal for what I'm trying to do is to expand upon this. I want to be able to go to the buffer overflow attack and see if there's any way that I can further exploit the system and maybe gain access to a shell or the operating system through those exploits. I'm still looking for some more exploits in the wild, trying to see what other types of classes of vulnerabilities might exist, and obviously develop some defenses against those types of systems or those types of attacks. So, any questions?
All right, questions from the audience? Samantha.
The vulnerability that you found in your system, was there a particular, I guess, prevention that you came up with?
Which one? The third one?
The third one that you're talking about for the Spectrum Challenge.
Yeah, we just made sure to use just a binary and to make sure that it was within the valid range. So, I mean, it had a really simple fix, but the point is, like, I was doing it very quickly and completely missed the point. And the thought is that, with all of the software and all the systems that we have, that would be really easy to do in a real world system. So.
Other questions from the audience? One in the back?
Do you know of any research has been done into actually finding vulnerabilities in the SDR hardware itself? I know in radar systems, there's lots of vulnerabilities that exist, pulling range gates off target and stuff like that. But since SDRs are all using direct conversion receivers, has there any, exploits been researched?
In the hardware itself?
Yes, yes.
I don't know. I'm coming at this from a software perspective purely. I might get into some of the FPGA stuff, but I'll probably never touch the hardware, so I don't know.
Okay, unless there's any others, we are out of time. So thank you so much, Seth.